Now we are going to graph the feasible region. Our feasible region is contained within these three constraints in this area. The final line that we've graphed is the isocontour line for z equal to 15. This shows us the direction of improvement. Now that we've graphed our feasible region, it's time to start the simplex method. But first, we need to put our original problem into standard form. So the first matrix we make is our constraint matrix, where we summarize our technological coefficients. Our right-hand side vector consists of these, our right-hand side. We're going to choose our initial basis. We're going to use the select variables as the initial basis for ease in calculation. So we need to partition A, our constraint matrix, into basic and non-basic variables. And then we're going to do the same thing over here with our decision variables. And we're just going to divide this. This right here is our cost coefficient matrix. So we have the cost coefficients here, and we're going to divide those into basic and non-basic again. Okay, so now we're at step 0 in tableau form. Step 0 is just like step 0 in matrix form, except that we're going to set up our tableau just the same way that we did our matrices. So now that we have our tableau set up, we need to decide what our basic variables are going to be. So we are going to use the variables that have all but one element in their column as a 0, and that extra element is a 1. So as you can see, that's going to be these three columns here. So that means that x3, x4, and x5 are going to be our basic variables. So we're now at step 1 in matrix form. We need to solve for xb and z given our current set of basic variables. So in order to find xb, we simply do b inverse times b. Z is equal to our basic cost coefficients times our basic technological coefficient, which is equal to 0. So now what we're going to do is move on to step 2, which is to test for optimality. Can we find a better z value? So for each non-basic decision variable, we're going to calculate zj minus cj, our reduced cost, which is equal to cb, b inverse aj minus cj. So for x1, all of this together is equal to -5. So now we're just going to do the same thing for x2. So using Danzig's rule, we want to find the index such that for a maximization problem, zt minus ct is the minimum zj minus cj. So the smallest answer that we got was -6, which means that our t value, or our index, is 2, which means that x2 should enter the basis. Now, this is step 2 in tableau form. x2 should enter the basis because -6 is the smallest number on our row 0. This is similar to our step 2 in matrix form. So we're now at step 3 in matrix form of the simplex method, which is to test for unboundedness. As you can see, we have an equation here. AT hat is equal to B inverse AT. And what we want is for AT hat to be greater than 0. If AT hat is less than or equal to 0, our problem is unbounded. So we've calculated A2 hat, which is, we're looking for the variable x2 to enter the basis. And as you can see, not every element of our matrix or vector is less than 0, which means that this problem is not unbounded and that we're good to continue working. So step 3 in tableau form is very similar to step 3 in matrix form. We are testing for unboundedness, and we simply need to verify that not every element of x2 is less than 0. And as you can see in our column here, not every element of x2 is less than 0. So now we are at step 4 in matrix form of the simplex method, where we have to choose the leaving or blocking variable. You'll notice that I haven't left room to calculate B3 hat over A32 hat, and the reason why is because A32 hat is less than 0, and therefore x4 will be leaving the basis. So we're now at step 4 in tableau form of the simplex method, You'll see that I've added an extra column to our tableau to perform the ratio test. So what we do is we divide the right-hand side value by its corresponding x2 values. So here we can see that our minimum value is 3. So after circling this row, we want to choose the basic variable that has a 1 in this row, in this case x4. And so now we know that x4 will be leaving the basis. So to show that x2 has entered the basis, we perform a pivot operation on the double circled element in our tableau, this element. So to achieve this, we are going to utilize elementary row operations. This gives us this new tableau, which has x2, x3, and x5 as our basic variables.
So for our iteration 2, these are our new basic variables, and these are our new non-basic variables. This gives us a B matrix here, and if we take the inverse of that matrix, this is what we'll be using. Down here are our cost variables for basic, and cost variables for non-basic, and this is our new in matrix. For step 1, we need to solve for x, b, and z. xb, we take b inverse times b. It gives us our inverse b times b. This is our xb matrix. Now we put that into z right here, and then using our cost variables for basic, multiply these out, and we get 18. In step 2, we're doing our test for optimality. We're looking for the minimum value of zj minus cj. First, we go to z1 minus c1 equals negative 23. We do the same thing for z4 minus c4 equals 6. The minimum value between these two is 23, so z1 minus c1 is the minimum. And this is not optimal because z1 minus c1 is still less than 0. We're seeing that not every element in a hat is less than 0, and we see after we work it out that it is not unbounded. And we're looking for the minimum value of bi hat over aik hat, but given that aik is greater than 0. And as we know from step 3, a2 and a3 are both less than 0, so a1 is the only one we can use, and when we work that out, we find out that x3 is leaving. For a tableau method, we have the very basic variables x3, x2, and x5. We know that we're not optimal because there is a value less than 0 in row 0. Because negative 23 is the smallest value, we know x1 is going to exit the basis. We know x1 is not unbounded because not every element in x1 is less than 0. Next, we need to do the ratio test for x3, x2, and x5. But we know we can only do the ratio test for x3 because the denominator needs to be greater than 0, and in x2 and x5 the denominator would be less than 0. So we do the ratio test. We have 28 over 17. And so we circle this row. So we know x3 is going to leave the basis. Now we're going to do a pivot operation on this element. After performing our pivot operation, the reduced costs of the non-basic variables are all positive, so the current basis is optimal. This can be read from the right-hand side column, right here. So this is our optimal solution. So for iteration 3, these are our new basic variables and our new non-basic variables. Here's our matrix B for our basic variables, and if we take the inverse of that, this is the one we'll be using. Here's our cost coefficients for our basic variables and our cost coefficients for our non-basic variables. This is our new non-basic variable matrix. So in step 1, we're going to solve for x, b, and z again. Solving for xb, b inverse b, we plug and chug, get these numbers. This is our resulting xb matrix. We put that into z, we do the same thing, and this is our value for z. In step 2, we're doing our test for optimality, and we're calculating the reduced costs for x3 and x4. Our reduced cost for x3 is going to give us 23 over 17, and our reduced cost for x4 is going to give us 10 over 17. Since our reduced costs for x4 and x3 are both greater than 0, there are no other alternative solutions. So our optimal solution is this.